Let's take a look at the pressure as a function of depth or height in our atmosphere. At sea level, we know that the atmospheric pressure is 101 kilopascals. What would the pressure be at a typical airplane cruising altitude of 12 kilometers? The barometric equation gives us a way to compare the pressure at these two heights. In order to fill in the details of the exponential, we will assume that the atmosphere has a temperature of 20 degrees Celsius. We will need to change that to Kelvin, though, for this formula. We also need the mass of a gas molecule. A nitrogen molecule has a mass of 4.7 times 10 to the minus 26 kilograms. So let's use this value for m. Finally, the constant K sub b, Boltzmann's constant, is 1.38 times 10 to the minus 23 joules per kilogram. You'll be able to find this value on your formula sheet. Alright, let's make sure everything is converted to base SI units before inserting it into the barometric equation. Using these values, the exponential term evaluates to about 0.26. When using the barometric equation, we are comparing these two pressures. So we can interpret our result to say that the pressure at 12 kilometers is about 26% of the sea level pressure. Of course, we can also directly calculate this pressure, which works out to be about 26 kilopascals. It's worth noting that these pressures are absolute pressures, not gauge pressures. Now, in comparison to pressure changes in a liquid, here we see that the pressure changes much more gradually with depth. Starting from up above, a descent of 12,000 meters only increases the pressure by a factor of 4. By comparison, you only need to swim about 40 meters below the surface of the ocean in order to quadruple the pressure.